July 10th, 1942. 14:35 hours. Akutan Island, Alaska Territory. Aviation machinist mate first class Albert Knack, 24 years old from Chicago, Illinois, pressed his face against the cold observation window of the PBY-5 A Catalina flying boat. Below, through breaks in perpetual fog that shrouded the Aleutian Islands, something impossible caught his eye. Red circles on wings. The rising sun emblem of Imperial Japan. A Zero fighter. The terror of the Pacific skies. Sitting upside down in marsh grass, apparently intact. Knack's hands trembled as he adjusted the binoculars. For 13 months since Pearl Harbor, this aircraft had been the nightmare of every American pilot from Hawaii to Burma. At Pearl Harbor, Zeros had destroyed American aircraft on the ground before they could fight back. Over the Philippines, they had massacred obsolete American fighters. In Burma, they had shot down everything the British could put in the air. The official American tactical doctrine when encountering a Zero was simple, humiliating, and brutally honest. Run away. Do not engage. Do not attempt a dogfight. Survive. Lieutenant William Thies, 28, from Seattle, Washington, piloted the Catalina through the fog banks. He had become disoriented in the weather, a common occurrence in the Aleutians where visibility could drop to zero in seconds. By dead reckoning and considerable luck, he had reoriented over the Shumagen Islands and chosen a direct route back to Dutch Harbor Naval Operating Base. That route took him directly over Akutan Island, a path rarely flown, a course that would change the Pacific War. Thies banked the Catalina into a tight circle. Once, twice, 3 times. Both men stared at the wreckage, unable to believe what they were seeing. No Japanese pilot would abandon such a prize. The Zero was Japan's most closely guarded military secret. Downed pilots were under explicit orders to destroy their aircraft rather than allow capture. Yet here one sat, apparently complete except for being inverted, in an Alaskan marsh that American forces controlled. Neither Knack nor Thies could have known they had just discovered what naval historians would later call a prize almost beyond value to the United States. What they were about to recover would expose the most profound paradox in aircraft design philosophy of World War II, a paradox written not in engineering diagrams, but in the lives saved in battles won through understanding a single enemy fighter. The Zero's reputation had been built on terror and respect in equal measure. In the 7 months since Pearl Harbor, American pilots had encountered an aircraft that defied every assumption about Japanese industrial capability. It was fast, faster than most American fighters. It was maneuverable, capable of turns that seemed to violate physics. It had range, escort missions over distances that no American fighter could match. And it was deadly, armed with 2 20mm cannon and 2 7.7mm machine guns that could shred American aircraft with devastating efficiency. The numbers told a story of dominance that seemed unbreakable. In early 1942 engagements over China, Zeros had achieved kill ratios as high as 12-1 against Soviet-built I-15 and I-16 fighters. In April 1942, a Japanese strike force, including 36 Zeros, had attacked Colombo, Ceylon, shooting down 27 British aircraft for the loss of 5 Japanese planes, a 5-1 ratio against experienced Royal Air Force pilots flying Hurricane and Fulmar fighters. At the Battle of the Java Sea in February, Zeros had massacred Dutch and British fighters attempting to defend the doomed Allied fleet. American fighter pilots had learned through bitter experience that traditional aerial combat tactics did not work against Zeros. The aircraft could outturn anything in Allied inventory. Attempting a turning dogfight with a Zero was suicide. Pilots who tried died. Those who survived did so by running, diving away at full throttle, using superior speed in a dive to open distance, then fleeing at low altitude where the Zero's advantages were minimized. But running was not a strategy. It was survival, temporary and unsustainable. The United States could not win air superiority in the Pacific by fleeing every engagement. American pilots needed answers. They needed to understand the Zero's capabilities and, more critically, its limitations. And on this foggy July afternoon, those answers lay inverted in Alaskan marsh grass, waiting to be discovered. 35 days earlier, on June 4th, 1942, the same day as the pivotal battle of Midway 1,500 miles to the south, Flight Petty Officer Tadayoshi Koga, 19 years old from Ibaraki Prefecture, Japan, had launched from a Japanese aircraft carrier Ryujo as part of a diversionary strike against American forces in the Aleutian Islands. Koga was young, but he was not inexperienced. He had completed advanced fighter training at the prestigious Chuchiura Naval Air Group, where only the most skilled pilots were assigned. He had logged over 300 flight hours in Zero, mastering the aircraft's sensitive controls and learning to exploit its extraordinary maneuverability. He was assigned to the Ryujo's fighter squadron specifically because his instructors had identified him as one of the most promising pilots of his class. The mission was straightforward. Strike Dutch Harbor Naval Operating Base on Unalaska Island, destroy American aircraft and facilities, draw American attention northward while the main Japanese fleet attacked Midway. Koga flew as part of a three-plane section assigned to strafe whatever targets they could find. His wingmen were Chief Petty Officer Makoto Endo, 24, and Petty Officer Tsugo Shikata, 22, both veterans with combat experience over China and the Dutch East Indies. The strike force approached Dutch Harbor through typical Aleutian weather: fog, low clouds, limited visibility. They descended through the overcast and found the bay spread below them. Ships in harbor, aircraft on the ground, buildings clustered around the waterfront. Koga and his section mates rolled into their strafing runs. The attack was devastating. Koga's 20mm cannon fire walked across a PBY. 5, a Catalina flying boat taxiing on the water. The aircraft exploded, burning fuel spreading across the harbor surface. He continued his run, strafing survivors in the water, a brutal but standard practice in Pacific air combat, where no quarter was given and none expected. His 7.7mm machine gun stitched lines of impacts across fuel storage tanks and wooden structures. Then something changed. Small arms fire erupted from defensive positions around the harbor, Marines and Navy personnel firing rifles and machine guns at the attacking aircraft. Most bullets missed, passing harmlessly through empty air. But one round, fired by an unknown American defender, struck Koga Zero. The bullet, probably .30 caliber from a Browning M1919 machine gun, severed an oil pressure line in the engine compartment. The damage was not immediately catastrophic. The engine continued running. Oil pressure dropped gradually rather than instantly. Koga completed his strafing run and climbed away from the harbor, following Endo and Shikata as they reformed their section. But as they turned west toward their carrier, Koga noticed his oil pressure gauge dropping steadily. He tapped the gauge, hoping it was a malfunction. The needle continued falling. Loss of engine oil meant engine seizure within minutes. Without oil, friction would generate heat beyond tolerance. Metal would expand, bind, and fail. The engine would stop, and over the frigid North Pacific, a stopped engine meant death. No pilot could survive more than a few minutes in water that cold. Koga signaled his wingmen with hand gestures. The Zero's radio equipment was minimal, designed to save weight. He pointed to his oil pressure gauge, then indicated the direction of Akutan Island. Japanese planners had designated the island as an emergency landing field before the operation. A submarine was stationed offshore specifically to rescue downed pilots. If Koga could reach Akutan and land safely, he would be recovered and returned to his carrier. The flight to Akutan took 6 minutes. That must have felt like hours. Koga watched his oil pressure gauge drop toward zero, while his engine temperature climbed. The Nakajima Sakae radial engine continued running. Japanese engineering was excellent, but it would not run much longer. Below, through scattered clouds, he could see Akutan Island's rocky coastline. He descended carefully, conserving altitude in case the engine failed. At 1,500 feet, he spotted what looked like a perfect landing field, a flat, grassy area about half a mile inland from Broadbight, a small bay on the island's eastern shore. The grass appeared firm, solid, inviting. From altitude, it looked like an ideal emergency landing site. Shikata and Endo circled overhead, watching their young wingmen's approach. Shikata, the more experienced pilot, suddenly noticed something that filled him with dread: water glistening between the grass stalks. The field was not solid ground but marshland, wet, soft terrain that would not support an aircraft's weight. He frantically tried to signal Koga, waving his arms in the cockpit, pointing downward, trying to communicate that the landing should be made gear up, belly landing on the grass rather than wheels down. But it was too late. Koga had already committed to his landing approach. His landing gear was down and locked. His flaps were extended. He was descending at 70 knots, lined up perfectly with what he believed was a grass runway. His attention was focused on maintaining proper airspeed and landing attitude, the concentration required for any landing, especially with a failing engine. At 15:42 hours, Koga Zero touched down. The main landing gear wheels made contact with grass, then immediately sank into soft mud beneath. The aircraft momentum carried it forward even as the wheels caught in the marsh. The nose dropped. The tail rose. For one moment, the Zero seemed to balance on its nose gear vertical before toppling forward completely. The aircraft inverted with tremendous force, flipping end over end. The impact was devastating. Koga, strapped in his seat, was thrown forward against his restraints as the Zero came to rest upside down. The force of the impact snapped his neck instantly. Death was immediate. The 19-year-old pilot from Ibaraki Prefecture died in an Alaskan marsh, far from home, far from his carrier, a casualty of a single bullet through an oil line. Endo and Shikata circled the wreckage, torn by impossible choices. Every Japanese pilot carried explicit orders to destroy any Zero that crash-landed in enemy territory. The aircraft's secrets were too valuable, its capabilities too sensitive to allow capture. But Koga might still be alive. They had not seen him exit the aircraft. He could be trapped, injured, waiting for rescue. They circled for 10 agonizing minutes, descending as low as they dared, trying to see movement near the wreckage. They saw none. Their fuel gauges showed reserves dropping toward minimum. Weather was closing in, fog rolling across the island, visibility deteriorating. Finally, with no signs of life and fuel becoming critical, they made the hardest decision of their military careers. They turned west toward the Ryujo, leaving their wingman behind, believing the designated submarine will recover him within hours. The submarine searched for Koga that night and the following day. But the USS Williamson, an American destroyer patrolling the area, detected the submarine's presence and drove it away with depth charges. The Japanese vessel withdrew, unable to approach Akutan without risking destruction. Koga's body remained in his cockpit. The Zero sat undisturbed in its marsh, invisible from standard patrol routes, unknown to American forces. For 35 days, the most valuable intelligence prize in the Pacific theater sat in an Alaskan marsh, waiting to be discovered. While Koga Zero waited in solitude, American fighter pilots across the Pacific continued dying in aircraft that could not match the Japanese fighters' capabilities. The Grumman F-4 Wildcat was America's primary carrier-based fighter in mid-1942. It was a good aircraft, rugged, reliable, well-armed with 6.50 caliber machine guns. But against the Zero, it was outclassed in nearly every performance metric that mattered in aerial combat. The Wildcat's maximum speed was 318 miles per hour. The Zero could reach 331 miles per hour. Not a dramatic difference, but enough to matter in combat. More critically, the Zero could climb faster. At sea level, a Wildcat could climb at approximately 2,200 feet per minute. A Zero could climb at 3,300 feet per minute, 50% faster. In a dogfight, the aircraft that could climb fastest controlled the engagement, choosing when to attack and when to disengage. But the most devastating difference was maneuverability. The Wildcat had a wing loading of 28.6 pounds per square foot, the aircraft's weight divided by wing area. The Zero's wing loading was 24.3 pounds per square foot. Lower wing loading meant the Zero could turn tighter circles. In a turning dogfight, the Zero could get inside the Wildcat's turn radius, bringing guns to bear while the American pilot could only try desperately to evade. American pilots had learned these facts through experience measured in lives lost. At the Battle of the Coral Sea in May 1942, Wildcats had fought Zeros to a tactical draw, but only by refusing to dogfight, diving on Zeros with altitude advantage, making a single firing pass, then diving away before the Zeros could respond. At Midway on June 4th, Wildcats had defended the American carriers against overwhelming Japanese attacks, but suffered heavy losses doing so. The psychological impact on American pilots was profound. They were flying machines that could not win in fair combat. Survival required avoiding engagement or fighting only on favorable terms that the enemy might not grant. This was not cowardice. It was brutal realism, but it was devastating to morale. American fighter pilots were warriors who had trained to dominate aerial combat. Instead, they were learning to survive by running. Commander John Thatch, 37, from Arkansas, had developed a Thatch Weave defensive tactic before Koga's crash. First used successfully at Midway, the Thatch Weave involved two Wildcats flying side by side. When attacked, they would turn toward each other, weaving their flight paths in a scissors pattern. Pursuing Zeros would find themselves flying into the gun sights of the second Wildcat. The tactic worked, saving many American pilots' lives. But it was fundamentally defensive, a survival technique, not a path to air superiority. What American pilots needed, what commanders desperately wanted, was understanding. How did the Zero achieve its performance? What were its limits? What vulnerabilities could be exploited? Intelligence reports from pilots who had fought Zeros provided some information, but pilot observations in the chaos of combat were often incomplete or inaccurate. What was needed was the actual aircraft, intact, available for testing. And on July 10, 1942, when Albert Knack peered through the Catalina's window and saw red circles on wings, that wish was about to be granted. July 11, 1942, 9:15 hours. Lieutenant William Thieves returned to Akutan Island with a landing party, carried aboard 2 additional PBY Catalinas. The recovery team included Chief Aviation Pilot William Scarborough, 32, from Virginia, an experienced Navy pilot assigned specifically to assess the crash Zero. Also aboard were mechanics, Marines for security, and medical personnel in case the Japanese pilot had survived. The Catalinas landed in broad bight, engines churning the cold water as they taxied to shore. The recovery team waded through shallow surf, then hiked inland toward the marsh where the Zero waited. The terrain was treacherous, soft ground concealed by grass, with pools of standing water that could swallow a man to his thighs. Progress was slow, exhausting. After 40 minutes of struggling through the marsh, they reached the wreckage. The Zero lay inverted, wings and fuselage apparently intact despite the violent crash. The vertical stabilizer was bent. The propeller blades were twisted. The landing gear had sheared off, but the airframe itself appeared remarkably undamaged, a testament to the structural integrity of Japanese engineering. Scarborough approached the inverted cockpit cautiously, his .45 caliber pistol drawn. Japanese forces in the Aleutians had proven aggressive and unpredictable. The possibility of an ambush, however unlikely, had to be considered. He peered into the cockpit and saw Tadayoshi Koga's body, still strapped in the pilot's seat, hanging upside down from his harness. The young pilot's neck was broken, his head tilted at an unnatural angle. He had been dead for 35 days. The recovery team stood in silence, looking at the body of their enemy. War propaganda had dehumanized the Japanese, portraying them as fanatics, barely human, unworthy of sympathy. But here was a young man, barely more than a boy, who had flown a long way from home to fight in a war that had killed him in an Alaskan marsh. Scarborough felt an unexpected surge of empathy. This pilot was not so different from the young American aviators dying in the Pacific. All warriors, all following orders, all risking their lives for nations and causes beyond their individual control. "Get him out," Scarborough ordered. "We'll bury him properly." Marines carefully cut Koga free from his harness and removed his body from the cockpit. They found his personal effects, a photograph of a young woman, perhaps a sister, perhaps a sweetheart, and a small notebook with Japanese writing. These items were collected for intelligence analysis. The body was wrapped in a spare tarp. While the burial detail prepared a grave site, Scarborough began examining the Zero methodically. He walked around the inverted aircraft, noting every detail. The construction immediately struck him as unusual. The skin felt thin under his hands, not like the thick aluminum of American aircraft, but almost delicate, like a beer can. He tapped the fuselage and heard a hollow sound that seemed wrong for a combat aircraft. He examined the cockpit area, looking for armor plating. American fighters mounted thick steel plates behind the pilot's seat, armor weighing 40 to 60 pounds that protected against rear attacks. The Zero had nothing. The pilot's seat was a simple metal frame with a thin cushion. No armor, no protection whatsoever. A bullet from behind would pass through the seat and the pilot with equal ease. He inspected the windscreen. American fighters were beginning to incorporate armor glass, heavy transparent plates that could stop small arms fire. The Zero's windscreen was standard glass, perhaps slightly thicker than civilian aircraft, but offering no ballistic protection. A head-on attack that struck the windscreen would penetrate into the cockpit, killing or wounding the pilot instantly. Most shocking was the fuel system. Scarborough traced the fuel lines from the engine back to the main fuel tanks in the fuselage. The tanks were simple aluminum containers, thin-walled, completely unprotected. American aircraft used self-sealing fuel tanks, complex assemblies with multiple layers of rubber and fabric that would swell and seal when punctured, preventing fuel leakage and fire. These self-sealing tanks added substantial weight, reduced fuel capacity, and increased manufacturing complexity, but they saved pilots' lives. The Zero had no self-sealing protection whatsoever. A single incendiary bullet through a fuel tank would cause immediate catastrophic fire. The pilot would have seconds, perhaps not even that, to bail out before being consumed by flames. American pilots had reported Zeros bursting into fireballs from minimal damage. Now the reason was clear. unprotected fuel tanks. Scarborough stood back, trying to process what he was seeing. This aircraft violated every principle American designers believed essential for combat aircraft. Where was the pilot protection? Where was the fuel system redundancy? Where was the survivability built into the design? The Zero was fast and maneuverable, but it was also fundamentally fragile, a high-performance machine with no safety margin, no forgiveness for damage, no second chance for its pilot. He turned to Lieutenant Thies. This thing is a flying death trap. One bullet in the right place, and the pilot is dead. They've sacrificed everything for performance. Thies nodded slowly. Can we recover it? We need to try. This aircraft could tell us everything. Koga's body was buried with military honors on a small rise overlooking Broadbite. A Marine chaplain read from the New Testament, offering prayers for a fallen warrior regardless of nationality. Marines fired a 3-volley salute, not required for an enemy combatant, but offered as respect from one fighting man to another. The grave was marked with a simple wooden cross bearing no name, only the date of burial, July 11th, 1942. Recovery proved more difficult than anticipated. The Aleutian weather, notorious for its unpredictability and ferocity, frustrated 3 separate attempts. Fog rolled in without warning, reducing visibility to 0. Storms generated waves that made approaching the shore impossible. The Zero sat in its marsh, tantalizingly close but unreachable, for 4 more days. On July 12th, Lieutenant Robert Kermsey, 29, from Minnesota, led a second recovery attempt. His team reached the Zero, assessed the damage more thoroughly, and attempted to construct a sledge to drag the aircraft to the beach. But their recovery ship, a small tender, lost both anchors in rough seas and had to withdraw, leaving the team stranded overnight on Akutan. The Catalina that retrieved them the next morning could not carry the Zero's weight. Only personnel could be evacuated. Finally, on July 15th, conditions improved enough for a barge to reach Akutan shore. A construction crew accompanied the barge, bringing timbers and rope to build a proper sledge. They worked through the day, constructing a platform on heavy wooden runners. The Zero, even waterlogged and mud-covered, weighed surprisingly little. 8 men could lift one wing. The entire aircraft, fully loaded, weighed only 5,555 pounds, remarkably light for a combat fighter. They dragged the Zero through the marsh to the beach, a journey of half a mile that took 4 hours. Twice the sledge became mired in soft ground and had to be pried free with timbers used as levers. Finally, they reached firm ground. The barge's crane lifted the Zero aboard. It was secured with chains and covered with tarps to protect it from salt spray during the voyage. The USS St. Mihiel, a seaplane tender, received the Zero and transported it to Seattle, arriving August 1st, 1942. From Seattle, it traveled by barge to San Diego, reaching Naval Air Station North Island on August 12th. The journey had taken 32 days from initial discovery to arrival at the test facility. At North Island, the Zero was placed in a heavily guarded hangar. Military police established 24-hour security with orders to shoot anyone attempting unauthorized access. Every mechanic, pilot, and engineer on base wanted to see the legendary Japanese fighter. Many wanted souvenirs, a piece of the windscreen, a fragment of aluminum skin, a rivet from the wing. Security was necessary not just to prevent espionage, but to prevent well-meaning Americans from disassembling the aircraft piece by piece. Navy mechanics began repair work under the supervision of Lieutenant Commander Raymond H. Dahl, 34, from Iowa, an engineering specialist with extensive aircraft maintenance experience. Dahl's team approached the Zero with professional curiosity mixed with suspicion born of propaganda. They had been told Japanese aircraft were crude copies of Western designs, built with inferior materials and sloppy workmanship. They expected to find evidence of technological backwardness. What they found astonished them. The Zero was a masterpiece of lightweight engineering. Every component had been designed with obsessive attention to minimizing mass without sacrificing strength. The main wing spars were constructed from extra super derailleur, an advanced aluminum alloy containing zinc, copper, and magnesium. Developed by Sumitomo Metal Industries in 1936, this alloy was lighter and stronger than standard aircraft aluminum, though more prone to corrosion. The Japanese had countered the corrosion weakness with zinc chromate coating applied after fabrication. The metallurgy was sophisticated, equal to or ahead of American capabilities at the time. This was not crude imitation, but advanced materials science applied with precision. Structural components revealed ingenious weight-saving measures. The wings were permanently bonded to fuselage rather than attached with removable joints. This eliminated massive attachment fittings, saving substantial weight. The trade-off was maintenance complexity. Wing removal for major repairs would be extremely difficult. But for an aircraft designed for maximum performance, the weight savings justified the inconvenience. The aft fuselage detached just behind the cockpit for engine access, a compromise between weight minimization and maintenance practicality. Engine placement near the wing's leading edge allowed a shorter, lighter tail section while maintaining proper balance. Control surfaces used fabric covering where American designs employed heavier metal panels. Landing gear struts were narrower than American equivalents, saving weight but reducing ground stability. The cockpit framework was minimalist. Simple metal tubing, providing structure with minimal material. Visibility was excellent, giving the pilot nearly 360-degree view, but there was zero protection. No armor plate behind the seat. No armored glass in the windscreen. No structural reinforcement to absorb battle damage. The cockpit was designed solely for function, with survival left entirely to pilot skill and luck. As repairs progressed, Dahl's team documented every measurement. The A6M Model 210, the variant Koga had flown, weighed 3,704 pounds empty, with full fuel 130 gallons, ammunition, 60 rounds for each 20mm cannon, 680 rounds for each 7.7mm machine gun. Pilot and equipment. Combat weight reached 5,555 pounds. The Grumman F4F4 Wildcat, America's primary carrier fighter, weighed 5,895 pounds empty and 7,426 pounds fully loaded. The Zero was 1,871 pounds lighter than its primary opponent, nearly a ton of weight difference. That gap translated directly into performance advantages in every metric that mattered in aerial combat. Power-to-weight ratio told the story clearly. The Zero's Nakajima Sakai 12-14-cylinder radial engine produced 950 horsepower. The Wildcat's Pratt & Whitney R-1830 twin wasp generated 1,200 horsepower. The American fighter had 250 more horsepower, a 26% advantage. But the Wildcat also carried 1,871 more pounds, a 34% weight penalty. The Zero's power-to-weight ratio was decisively superior, 0.171 horsepower per pound versus 0.162 for the Wildcat. Wing loading was equally revealing. The Zero carried 24.3 pounds per square foot of wing area. The Wildcat carried 28.6 pounds per square foot. Lower wing loading meant the Zero could turn tighter, climb faster at low altitude, and maneuver more aggressively. In a turning dogfight, physics gave the Zero an insurmountable advantage. The American pilot could not outturn the Zero no matter how skilled he was. The aircraft simply could not match the tighter turn radius. But as Dahl's mechanics examined the fuel system more closely, they found the vulnerability that would become the key to defeating the Zero in combat. The fuel tanks were simple aluminum containers with no self-sealing capability whatsoever. A single bullet, even a pistol round, through a fuel tank meant immediate fire. There would be no gradual leak, no time to switch to backup tanks, no chance to limp home. There would be ignition, explosion, death. American pilots had reported Zeros exploding from minimal damage. Intelligence officers had suspected Japanese aircraft used inferior fuel that ignited more easily. The truth was simpler and more shocking. The fuel tanks themselves were vulnerable beyond anything acceptable in Western aircraft design. The repair team straightened the bent vertical stabilizer and rudder using hydraulic presses. They replaced the damaged wing tips, flaps, and canopy with components carefully fabricated to match original specifications. The landing gear, sheared off during the crash, required complete replacement, the most difficult repair, as no spare parts existed. Machinists manufactured new struts matching the original dimensions, working from measurements and photographs. The three-blade Sumitomo variable pitch propeller was damaged but reparable. Technicians dressed the blades, removing nicks and restoring proper contour. Even damaged, the propeller remained serviceable, further testament to Japanese manufacturing quality. By mid-September, the Zero was ready for flight testing. 68 days after Koga's crash, his aircraft would fly again, this time in American hands, revealing secrets that would help defeat the empire he had died serving. Lieutenant Commander Edward Eddie Sanders, 31, from Texas, was one of the Navy's most experienced test pilots in 1942. He had logged over 2,500 flight hours in dozens of different aircraft types, from trainers to bombers. He understood aircraft performance not just intuitively, but analytically. capable of precisely assessing handling characteristics, control response, and flight envelope limitations. On September 20th, 1942, Sanders climbed into the cockpit of the Akutan Zero for its first American test flight. He had read every intelligence report about the Zero's combat performance. He had debriefed pilots who had fought Zeros and survived. He knew the aircraft's reputation: fast, maneuverable, deadly. But reputation was not data. Sanders needed facts, measurements, limits. His life, and the lives of every American fighter pilot, depended on accurate assessment of this aircraft's true capabilities. The cockpit felt crammed compared to American fighters. Sanders was 6 feet tall and 200 pounds, large for a pilot. The Zero's cockpit had been designed for smaller Japanese pilots, typically 5 inches shorter and 40 pounds lighter. Sanders' knees pressed against the instrument panel. His head nearly touched the canopy. He noted immediately the excellent visibility. The canopy provided nearly unobstructed view in all directions, a significant advantage in combat, where seeing the enemy first often meant survival. The engine started smoothly. The Nakajima Sakae radial engine, despite its months of inactivity and saltwater exposure during recovery, ran with mechanical precision. Japanese engineering, whatever its other qualities, produced reliable power plants. Sanders checked his instruments methodically, confirming fuel pressure, oil pressure, coolant temperature, all within normal ranges. He taxied carefully, aware that the Zero's narrow-track landing gear made ground handling tricky. American fighters used wide-stance landing gear that provided excellent stability during taxi, takeoff, and landing. The Zero saved weight with narrower gear, but the trade-off was increased difficulty during ground operations. The aircraft wanted a ground loop. Swing nose first in a tight circle. If the pilot wasn't careful with rudder inputs, Sanders advanced the throttle. The Zero accelerated with surprising eagerness, gaining speed faster than he expected. The takeoff roll was remarkably short, approximately 500 feet, compared to 800 feet for a Wildcat. The aircraft lifted off smoothly at 65 knots and climbed with impressive authority. Within seconds, Sanders understood why American pilots feared this aircraft. The rate of climb was extraordinary, over 3,000 feet per minute sea level, 50% better than any American carrier fighter. At 8,000 feet, Sanders began systematic testing. He started with basic handling: level flight at cruise power, gentle turns left and right, climbs and descents. The controls felt light, almost sensitive. Small stick movements produced immediate aircraft response. After years flying American fighters with heavier control forces, the Zero felt almost delicate, like switching from a truck to a sports car. He pushed the throttle forward for maximum power runs. The Zero accelerated smoothly to approximately 330 miles per hour at 15,000 feet, faster than a Wildcat, but not dramatically so. The speed advantage was real but modest, perhaps 15 miles per hour. In combat, that margin could matter, but it wasn't decisive. Then Sanders attempted maneuvers that would reveal the Zero's true capabilities. He rolled the aircraft left, then right, then left again. The roll rate at cruise speed was excellent. The Zero snapped into rolls with minimal control input. But when he pushed the speed above 200 knots, 230 miles per hour, something changed. The ailerons, the control surfaces on the wing's trailing edge that produced roll, suddenly stiffened. The light, responsive controls became heavy, requiring excessive force on the stick to produce roll. Sanders tried rolling left, then right. The aircraft rolled left much easier than right. This asymmetry was crucial. In combat, a Zero pilot would naturally prefer left rolls. Knowing this, an American pilot could exploit the tendency, forcing the Zero into right rolls where it was slower and less responsive. More importantly, at high speed, the Zero lost its primary advantage. The aircraft that could outroll anything at 180 knots became sluggish and unresponsive at 250 knots. American fighters, heavier and more powerful, actually gained advantages as speed increased. If an American pilot could force combat into high-speed conditions, the Zero's maneuverability advantage disappeared. The next test was potentially lethal but absolutely necessary. Sanders put the Zero into a dive to gain speed, then pulled hard on the stick. Negative G-force, the sensation of being thrown against the restraining straps as the aircraft's nose pitched downward sharply. The engine coughed once, sputtered, and quit entirely. Silence except for windstream. Sanders was flying a glider at 5,000 feet over San Diego Bay. He maintained composure. Panic killed test pilots. He pushed the stick forward, leveling the aircraft's pitch attitude. The propeller windmilled in the airstream. After 3 seconds of level flight, the engine caught and restarted, running smoothly as if nothing had happened. Sanders repeated the test twice more with identical results. The Zero's carburetor, a float-type design that relied on gravity to deliver fuel to the engine, could not handle negative G-forces. Under negative acceleration, fuel flow stopped completely. The engine quit. Every time. Predictably, this was the answer American pilots desperately needed. When pursued by a Zero, the correct tactic was not turning or climbing. Both would favor the lighter, more maneuverable Japanese fighter. The correct tactic was pushing the stick forward hard, diving with negative G-force. The Zero's engine would quit instantly. The American fighter's pressure-type carburetor would continue delivering fuel. The engine would keep running. In those crucial seconds while the Zero's pilot struggled to restart his dead engine, the American pilot could open range and escape. Or, if he chose to exploit the momentary advantage, he could reverse climb and attack the Zero from behind while it was vulnerable. Sanders flew 24 test flights between September 20th and October 15th, 1942. Each flight revealed new details about the Zero's performance envelope. The famous maneuverability was real, but came with limitations. At low speeds, below 200 miles per hour, the Zero could turn inside any Allied fighter. Its low-wing loading and lightweight gave it a decisive advantage in slow-speed maneuvering. But at high speeds, above 250 miles per hour, the Zero became progressively less responsive. The aileron stiffened. Roll rate decreased dramatically. The elevator controls, which control pitch, also required more force at high speed. The Zero was designed for low to medium speed combat, where its light weight provided maximum advantage. At high speeds, heavier American fighters with more powerful engines gained the upper hand. Sanders compiled his findings into a technical report distributed to every fighter squadron in the Pacific. Pilots read with intense interest, finally understanding the enemy aircraft that had dominated Pacific skies for over a year. The report's tactical recommendations were clear and specific. Never attempt to dogfight a Zero below 250 miles per hour. The Zero will win every time. Its turn radius is tighter, its rate of climb is superior, and its low-speed handling is unmatched. Use diving attacks from altitude advantage. Gain altitude, spot the Zero below, dive at maximum speed, make a single high-speed firing pass, continue diving past the target, use superior diving speed to zoom back to altitude. Repeat as necessary. If caught at low altitude or low speed, push the stick forward immediately. Dive with negative G-force. The Zero's engine will quit. Your engine will continue running. Use those seconds to escape or reverse the engagement. Force combat into high-speed conditions. Above 250 miles per hour, the Zero's control surfaces stiffen, and its maneuverability advantage disappears. American fighters become competitive in roll rate and superior in diving speed. Never turn with a Zero. This cannot be emphasized enough. Attempting to outturn a Zero is suicide. The physics do not favor the heavier American aircraft. Use American advantages. Armor protection, diving speed, engine power at high speed, self-sealing fuel tanks that allow survival of battle damage. The psychological impact on American pilots was profound. For over a year, they had felt helpless against an apparently invincible enemy fighter. Now they had answers. They had tactics. They had hope. The Zero was not invincible. It was an excellent aircraft, brilliantly designed for specific combat conditions, but it had exploitable weaknesses. It could be defeated by pilots who understood its limitations and fought intelligently rather than attempting to match its strengths. Lieutenant Colonel Kenneth Walsh, 25, from New York, a Marine Corps pilot who would eventually be credited with 21 confirmed aerial victories and awarded the Medal of Honor, later stated that understanding the Zero's negative G vulnerability saved my life at least 3 times. Walsh survived encounters that would have been fatal without the tactical knowledge derived from testing the Akutan Zero. Commander William Leonard, 28, from New Jersey, who would retire as Rear Admiral with 6 confirmed victories, said the captured Zero was worth 100 times its weight in gold. To my knowledge, no other captured enemy machine has ever unlocked so many secrets at a time when the need was so great. The Akutan Zero's influence extended far beyond the 24 test flights Eddie Sanders conducted. The aircraft became a teaching tool, a research platform, and ultimately a weapon in itself, not through its guns, but through the knowledge it provided. In October 1942, the Zero was flown in mock combat against every American fighter type in operational service. Each engagement was carefully controlled, filmed from multiple angles, and extensively debriefed. The goal was not to determine which aircraft would win. That depended more on pilot skill than aircraft capability, but to identify specific tactical situations where each aircraft held advantages. Against the F-4F Wildcat, the Zero demonstrated overwhelming superiority in turning combat below 250 miles per hour. In a classic dogfight with both aircraft starting at the same altitude and speed, the Zero could get inside the Wildcat's turn radius within 2 complete circles. But when the Wildcat pilot used boom and zoom tactics, diving from altitude, making a high-speed pass, then climbing away, the engagement became far more balanced. The Wildcat could not be caught if it maintained energy and refused to slow down. Against the P-38 Lightning, a twin-engine heavy fighter with devastating firepower but inferior maneuverability, the test revealed that the Lightning's superior high-speed performance and dive characteristics made it nearly invulnerable to Zero attacks if properly flown. The P-38 pilot could engage or disengage at will, choosing when to fight and when to flee. The Zero could not catch a Lightning in a dive, could not keep up in level flight at high speed, and had no answer to Lightning pilots who maintained altitude and energy advantages. Against the P-40 Warhawk, results were mixed. The P-40 was slower than the Zero but could dive faster and had superior firepower. P-40 pilots learned to use slashing dive attacks, never getting slow, never attempting to turn with the Zero. This tactic, developed by Flying Tigers in China before the Akutan Zero was recovered, was validated and refined by testing against the captured aircraft. The most important finding was that American aircraft were competitive with the Zero when flown correctly. The Zero's advantages were real, but not overwhelming. Proper tactics neutralized most of its superiority. And American aircraft had compensating advantages: better pilot protection, better structural strength, better diving performance, better high-speed handling. Japanese military historian Masatake Okumiya, who served as a lieutenant commander in the Imperial Japanese Navy during the war and later became a lieutenant general in the Japan Air Self-Defense Force, wrote in his post-war analysis that the revelations from the Akutan Zero were as dire for the Japanese military as the loss at the Battle of Midway. We knew our most closely guarded fighter secrets had been compromised, but we had no way to counter the tactical innovations the Americans would develop from that knowledge. The most significant impact of the Akutan Zero was indirect but decisive. Validation of design choices in the F-6F Hellcat, the fighter that would ultimately dominate Pacific skies. Grumman Aircraft Engineering Corporation had begun designing the Hellcat before the Akutan Zero was recovered. The initial concept emerged from combat reports following the battles of Coral Sea and Midway in May and June 1942. Pilots reported that the Wildcat, while tough and reliable, lacked the speed and climb rate to compete effectively with Zeros. Grumman's chief designer, Leroy Grumman, 48, and his team set out to create a fighter that could match the Zero's performance while maintaining American advantages in protection and firepower. The first XF-6F-1 prototype made its maiden flight on June 26, 1942, 2 weeks before Koga crashed on Akutan. Design was already well advanced before American engineers could study the captured Zero. But the Hellcat's development benefited enormously from hard data provided by testing the Akutan aircraft. Grumman's design philosophy directly contradicted the Zero's approach. Where the Zero sacrificed protection for performance, the Hellcat would provide maximum pilot protection compatible with acceptable performance. Where the Zero minimized weight at all costs, the Hellcat would use weight strategically, armor and self-sealing tanks were non-negotiable, but the aircraft would still be fast enough to fight Zeros on favorable terms. The Hellcat that entered service in January 1943 incorporated lessons learned from understanding the Zero. The aircraft weighed 9,238 pounds empty, nearly twice the Zero's empty weight, but was powered by a Pratt & Whitney R-2800 double Wasp engine, producing 2,000 horsepower, more than double the Zero's power output. Maximum speed was 380 miles per hour, 50 miles per hour faster than the Zero. Rate of climb was 3,500 feet per minute at sea level, exceeding the Zero's climb rate despite being 75% heavier. The power-to-weight advantage of the massive R-2800 engine overcame the weight penalty of armor and protection. The Hellcat's design specifically exploited Zero weaknesses identified through testing the Akutan aircraft. The Hellcat excelled at high-speed combat, where Zeros were less maneuverable. It could dive faster than any Japanese fighter, allowing boom and zoom attacks with impunity. Its robust structure could sustain battle damage that would destroy a Zero. And critically, its pilot had armor protection, armor glass, and self-sealing fuel tanks that gave him a realistic chance of surviving hits that would kill a Zero pilot. When Hellcats entered combat in August 1943, the results were immediate and devastating to Japanese air power. During the Gilbert Islands campaign in November 1943, Hellcats shot down 30 Japanese aircraft for the loss of 3, a 10-to-1 kill ratio. At the Battle of the Philippine Sea in June 1944, the Great Marianas Turkey Shoot, Hellcats and other American fighters destroyed approximately 600 Japanese aircraft over 2 days, while losing fewer than 30 fighters in air-to-air combat. The kill ratio exceeded 20-to-1. These results reflected multiple factors: better pilot training, tactical air control, numerical superiority. But fundamentally, the Hellcat was designed with full knowledge of the Zero's capabilities and limitations. Grumman's engineers had studied the Akutan Zero's test data, understood where it excelled and where it struggled, and designed an aircraft optimized to fight Zeros on American terms. The Akutan Zero exposed a fundamental philosophical divide in aircraft design that transcended mere engineering decisions. It revealed different cultural assumptions about warfare, risk, and the value of human life. Japanese aircraft design philosophy in 1942 prioritized offensive capability above all else. The warrior accepted risk as inevitable. Bushido, the samurai code adapted to modern military service, emphasized attack, courage in the face of death, and acceptance of sacrifice. These cultural values translated directly into aircraft specifications. The Imperial Japanese Navy's requirements for what became the Zero specified maximum range, firepower, and maneuverability. Armor protection was not mentioned. Self-sealing fuel tanks were not required. The specifications implicitly assumed that pilot survival will be achieved through superior combat effectiveness, not through passive protection. A skilled pilot in a superior aircraft will win battles and survive. Protection systems were unnecessary weight that reduced performance. This philosophy worked brilliantly in 1941 and early 1942, when Japanese pilots were the best trained aviators in the world, flying the best fighter aircraft in service anywhere. Against obsolete Chinese, British, Dutch, and American aircraft, Zeros achieved spectacular kill ratios. Japanese pilots dominated through skill and superior equipment, but the philosophy contained a fatal flaw. It assumed the war would be short. Japan's strategy was based on striking decisively, achieving local superiority, and negotiating from strength before America's industrial capacity could be mobilized. In a short war lasting months, pilot attrition would not matter. What mattered was winning the initial battles. When the war did not end quickly, when it became a grinding 4-year attrition conflict, the lack of pilot protection became catastrophic. A Zero pilot shot down was almost certainly dead. No armor to stop bullets. No self-sealing tanks to prevent fire. No structural redundancy to absorb damage. One hit in a vital area meant death. American aircraft design philosophy made different assumptions. Pilot survival was paramount. The United States had the industrial capacity to build unlimited numbers of aircraft, but training skilled pilots took time. A pilot who survived being shot down could return to combat, bringing accumulated experience and improving with each mission. Therefore, protection systems justified their weight penalty. American fighters carried armor plate behind the pilot's seat, typically 40 to 60 pounds of hardened steel positioned to stop bullets and shell fragments from rear attacks. They used armored glass windscreens, heavy transparent plates that could stop small arms fire from head-on attacks. Most importantly, they incorporated self-sealing fuel tanks. Self-sealing tank technology had been developed in Britain and adopted by American manufacturers in 1940. The system used multiple layers: an outer layer of untreated rubber, a middle layer of vulcanized fabric, and an inner layer that swelled when exposed to fuel. When a bullet punctured the tank, fuel contacted the inner layer, causing it to expand and seal the hole. The system was not perfect. Large holes might not seal completely, but it dramatically reduced the probability of catastrophic fire. These protection systems added substantial weight. A self-sealing fuel tank system weighed approximately 30% more than a standard aluminum tank of equivalent capacity. Armor plates and armored glass added another 100 to 150 pounds, depending on the aircraft. Control surfaces were reinforced. Structure was built more robustly. Overall, American fighters were typically 15 to 30% heavier than comparable Japanese fighters with similar engine power. But American pilots survived battle damage. A Wildcat pilot might be hit multiple times, sustain wounds, have his aircraft shot full of holes, and still make it back to his carrier. The armor stopped bullets that would have killed him. The self-sealing tanks prevented fire. The robust structure held together despite damage. The pilot survived, received medical treatment, healed, and returned to combat. Japanese pilots and Zeros had no such chances. A single bullet through the fuel tank meant fire. A single bullet through the unarmored seat meant death or crippling injury. The lightweight structure crumpled under battle damage that American aircraft could absorb. Japanese pilots who bailed out over water often drowned before rescue arrived because they lacked the flotation equipment American pilots carried routinely. The statistical result was devastating for Japan. In 1942, Japanese and American pilots were roughly equal in skill, with Japanese pilots holding a slight advantage from pre-war combat experience in China. By mid-1943, American pilots held a decisive skill advantage because they survived long enough to become experienced. The average American fighter pilot by 1944 had hundreds of hours of combat experience. The average Japanese replacement pilot had minimal training and often died in his first combat mission. The mathematics of attrition favored a side that protected its pilots. Japan could build aircraft faster than it could train replacement pilots. America could train pilots faster than Japan could build replacement aircraft. The side that kept its pilots alive won the war of attrition. By late 1944, the Zero's transformation from air superiority fighter to suicide weapon symbolized complete failure of its design philosophy. In October 1944, during the Battle of Leyte Gulf in the Philippines, Vice Admiral Takejiro Nishi, 54, commander of the 1st Air Fleet, organized the first official kamikaze unit. The concept was simple and horrifying: deliberately crash aircraft into enemy ships, using the fighter as a guided missile, with the pilot becoming a human warhead. The Zero was used more than any other aircraft type for kamikaze missions. Its long range allowed it to reach distant targets. Its maneuverability helped evade defensive fire during the final approach. And tragically, its lightweight construction, the same design feature that made it vulnerable in combat, meant it could be mass-produced quickly enough to sustain suicide operations. Pilots selected for kamikaze missions received minimal training. They needed only to take off, navigate to the target, and dive into a ship. Combat skills were irrelevant. They would not return. The Zero, designed to dominate dogfights over China, ended its career as a disposable weapon piloted by inadequately trained teenagers flying one-way missions. The kamikaze campaign inflicted significant damage on American naval forces. Approximately 3,800 Japanese pilots died in kamikaze attacks between October 1944 and August 1945, sinking or damaging over 300 Allied ships. But the strategy was fundamentally defensive and desperate, an acknowledgement that Japanese aircraft could no longer compete in conventional air combat. The psychological contrast with the Zero's initial role was stark. In 1941, the Zero had been the symbol of Japanese air power supremacy, flown by elite pilots, feared throughout the Pacific. By 1945, it was being flown by undertrained pilots on suicide missions because it could not survive conventional combat against American fighters. In November 1943, the Akutan Zero was displayed at Washington National Airport during celebrations of the 25th anniversary of airmail service. The aircraft was presented as a war trophy, proof that American forces had captured and studied the enemy's most formidable fighter. Thousands of civilians viewed the Zero, many seeing for the first time the aircraft their sons and brothers faced in combat. The display served propaganda purposes, but also educated the public about the nature of the enemy's military technology. The Zero looked sleek, predatory, dangerous, the physical embodiment of Japanese military aggression. Few viewers understood they were looking at a fundamentally flawed design, an aircraft that prioritized performance over pilot survival to a degree that American engineers considered irrational. In 1944, the Akutan Zero was returned to NAS North Island for continued use as a training aircraft. New fighter pilots flew against it in controlled combat, learning firsthand how Zeros maneuvered, where they excelled, where they struggled. A second captured Zero, an A6M Model 52, recovered during the liberation of Guam, joined the training program, allowing direct comparison between early and late Zero variants. These training flights provided American pilots with invaluable experience before they faced real Zeros in combat. Pilots learned to recognize the distinctive elliptical wingtips, the sound of the Nakajima Sakai engine. The Zeros preferred attack patterns. They practiced a negative G pushover maneuver until it became instinctive. They learned boom and zoom tactics against an actual Zero, rather than simulating attacks against American fighters painted with Japanese markings. The training program undoubtedly saved hundreds of American lives by preparing pilots for the specific challenges of fighting Zeros. Knowing intellectually that the Zero's engine would quit under -G was different from experiencing it firsthand in control conditions where a mistake would not be fatal. On February 4th, 1945, the Akutan Zero's operational life ended ignominiously. Lieutenant Commander Richard Cromlin, 32, from Alabama, was taxiing the Zero at NAS North Island when a Curtiss SB-2C Helldiver dive bomber collided with it during ground operations. The impact destroyed the Zero's tail section and damaged the fuselage beyond economical repair. The aircraft was scrapped shortly thereafter. Its intelligence value had been fully extracted through test flights, technical analysis, and training operations. It had served its purpose completely. But the lessons it taught lived on in tactical manuals, pilot training curricula, and the design of American fighters that dominated Pacific skies through war's end. Assessing the Akutan Zero's strategic impact requires examining multiple levels: tactical, operational, and psychological. At the tactical level, the impact was immediate and quantifiable. American fighter squadrons that received tactical bulletins based on the Zero's test flights began achieving better kill ratios against Japanese fighters within weeks. Pilots who had been taught to fear the Zero learned to respect it while understanding its limitations. The change in mindset was as important as the specific tactical information. Marine Corps squadrons at Guadalcanal in late 1942 and early 1943 began using -G escape maneuvers routinely when pursued by Zeros. Wildcat pilots who would previously have attempted to outturn the Zero, often with fatal results, now pushed over into -G dives that left their pursuers with dead engines and no way to continue the attack. Survival rates improved measurably. Navy fighter squadrons in the Solomon Islands campaign adopted boom and zoom tactics almost universally after receiving detailed performance data from the Akutan Zero tests. The tactic required discipline, resisting the temptation to engage in turning combat, even when it seemed the Zero was vulnerable, but pilots who followed doctrine survived and achieved kills. Those who reverted to dogfighting died. At the operational level, the Akutan Zero influenced aircraft development programs. The Hellcats design benefited from validation of protective features. Grumman's engineers could confirm that armor, self-sealing tanks, and robust structure were not luxuries, but necessities that did not compromise performance unacceptably when paired with sufficient engine power. The Vought F4U Corsair, which entered service in late 1942, incorporated similar lessons. The Corsair was even heavier than Hellcat, 9,900 pounds empty, but was powered by the same R-2800 engine producing 2,000 horsepower. Maximum speed exceeded 400 miles per hour. The Corsair could fight Zeros on highly favorable terms, using speed and power to dominate engagements while providing pilots with comprehensive protection. Later American fighters, the Grumman F-8F Bearcat and the Republic P-47 Thunderbolt, continued to trend toward heavily armored, powerfully engined aircraft that prioritized pilot survival alongside combat effectiveness. American designers never again questioned whether protection systems justified their weight penalties. The answer was clear. Pilots who survived became more effective with experience, and that accumulating expertise was more valuable than marginal performance improvements from weight reduction. At the psychological level, the Akutan Zero's impact was transformative. American pilots in mid-1942 had felt outclassed and helpless. Japanese fighters were faster, more maneuverable, and flown by experienced pilots who seemed invincible. The captured Zero demonstrated that Japanese engineering, while sophisticated, was not magical. The Zero could be understood, its weaknesses could be exploited, and most importantly, it could be defeated. This psychological shift from fear to confidence cannot be overestimated. Pilots who believe they cannot win tend to fulfill that belief through hesitancy, defensive flying, and failure to press attacks. Pilots who believe they have the tools and tactics to win fight more aggressively, take calculated risks, and achieve better results. The Akutan Zero gave American pilots the confidence that came from knowledge. When Japanese military intelligence learned that an intact Zero had been captured, the reaction was panic mixed with resignation. They knew what it meant. The Zero's combat dominance had been built partly on mystery. American pilots did not fully understand how the Zero achieved its performance, what limitations it had, or how to exploit vulnerabilities. That mystery magnified the Zero's effectiveness beyond its actual capabilities. Combat reports from pilots who survived Zero encounters often exaggerated the Japanese fighter's performance out of honest misperception or traumatic stress. The Zero became a bogeyman, credited with capabilities it did not actually possess. Once the mystery was dispelled, once American engineers could measure precise performance figures and test pilots could discover exact limitations, the psychological advantage disappeared. Japanese commanders understood that American tactical doctrine would adapt quickly once hard data became available. The Imperial Japanese Navy attempted to accelerate development of replacement fighters. The Mitsubishi J-2M Raiden Thunderbolt was designed as a high-speed interceptor to counter American bombers and fight the new generation of American fighters on more equal terms. But development was slow, production was limited by resource shortages, and the aircraft entered service too late and in too small numbers to affect the war's outcome. Engineers attempted to improve the Zero itself. The A6M Model 52 variant, introduced in 1943, incorporated modest protective improvements. 55mm armor glass windscreen and 8mm armor plate behind the pilot seat. Engine power increased slightly to 1,130 horsepower with the improved Sakai 21 engine. But these modifications increased weight by 28%, from 5,313 pounds to 6,025 pounds, while horsepower increased only 16%. The result was an aircraft slower and less maneuverable than the original A6M2 that Koga had flown, without gaining compensating advantages. Later Zero variants became progressively less effective as American fighters became progressively more capable. By 1944, the performance gap had widened to the point where Zeros were obsolete by current standards. The A6M Model 52 could reach 351 miles per hour, barely faster than the original model, while the Hellcat could exceed 380 miles per hour, and the Corsair could reach 417 miles per hour. Japanese engineers faced an impossible dilemma. They understood that protection systems were necessary. Combat attrition of pilots was unsustainable, but adding armor and self-sealing tanks required more powerful engines to maintain performance, and Japan lacked the industrial capacity to develop and mass-produce engines comparable to American power plants. The Nakajima Hamar engine, intended to produce 1,800 horsepower, suffered from reliability problems and never achieved its design performance. Japan's most powerful operational engine by war's end was the Mitsubishi Kase, producing 1,560 horsepower, respectable but still far short of the two 000+ horsepower American engines. The result was a gap that widened month by month. American fighters became faster, better protected, and more heavily armed, while Japanese fighters stagnated or even regressed as attempted improvements added weight without corresponding performance gains. The human cost of the Zero's design philosophy became starkly apparent as the war progressed. Japanese pilot casualties reached catastrophic levels by 1944. In 1941, the Imperial Japanese Navy had approximately 3,000 fully trained carrier aviators, pilots with hundreds of flight hours and extensive combat experience from operations in China. These men represented a decade of intensive training, selected from thousands of candidates, refined to the most rigorous flight curriculum in the world. They were the elite of Japanese military aviation. By the end of 1942, approximately 40% of these pre-war trained pilots were dead. They'd been killed in combat over Pearl Harbor, the Philippines, the Dutch East Indies, Ceylon, the Coral Sea, Midway, and Guadalcanal. The pilots who replaced them had less training. The pipeline could not sustain the pre-war standards while also replacing combat losses. By mid-1943, the average Japanese replacement pilot had perhaps 100 hours of flight training before assignment to operational units. American pilots received over 300 hours of training before entering combat. The training gap meant Japanese pilots were entering combat unprepared, flying aircraft that offered zero protection if they made mistakes. By late 1944, some Japanese pilots received as little as 40 hours of training, barely enough to take off, fly basic maneuvers, and land. They were sent into combat against American pilots who often had hundreds of hours of combat experience, flying superior aircraft, using tactics refined through years of warfare. The outcome was predictable and horrific. At the Battle of the Philippine Sea in June 1944, American pilots described shooting down Japanese aircraft that barely attempted to maneuver. Some Japanese pilots seemed not to see their attackers until bullets were striking their aircraft. The Marianas Turkey shoot was less a battle than a massacre. Inexperienced Japanese pilots flying obsolescent Zeros against veteran American pilots in Hellcats and Corsairs. Over 600 Japanese aircraft were shot down in 2 days. The Zero's lack of protection compounded the slaughter. American pilots survived being shot down with increasing frequency as rescue operations became more sophisticated. Japanese pilots flying Zeros had no such chances. A Zero hit in the fuel tanks exploded. A pilot wounded in the unprotected cockpit often died before he could bail out. Those who did bailout often drowned because they lacked adequate flotation equipment. The mathematics were brutal. American pilot survival rate after being shot down was approximately 40%. Japanese pilot survival rate after being shot down in a Zero was approximately 10%. Over hundreds of engagements, the survival differential accumulated into a decisive American advantage in experienced pilots. By war's end in August 1945, the Imperial Japanese Navy had lost approximately 20,000 pilots killed in action. The majority died in aircraft that offered no protection, no second chance, no margin for error. The Zero that had seemed so advanced in 1941 had become a death trap by 1944. After Japan's surrender in August 1945, American technical intelligence teams interviewed surviving Japanese aircraft designers and engineers. Their testimony provided context for decisions that, viewed from 1945, seemed irrational. Jiro Horikoshi, 42, the Zero's chief designer, stated in post-war interviews that armor protection and self-sealing tanks were never mentioned in the original 1937 Navy specifications for what became the Zero. The requirements emphasized range, maneuverability, and firepower. Weight restrictions were severe. The entire aircraft was not to exceed 6,000 pounds loaded. Given available engine technology producing only 950 horsepower, meeting the requirements while including protection systems was impossible. Horikoshi made a conscious choice. Meet the specified requirements by eliminating everything not explicitly required. Armor was not required. Self-sealing tanks were not required. Therefore, they were omitted. The weight save went into fuel capacity, enabling the extraordinary range that allowed Zeros to escort bombers over distances no other fighter could match in 1941. The decision was rational given the strategic assumptions prevailing in 1937 to 1940. Japan expected a short war with China, followed by potential short conflicts with Western powers. In a short war, pilot attrition would not matter. What mattered was winning the initial battles decisively. The Zero was optimized for that scenario. When the scenario proved wrong, when the war became a grinding 4-year attrition conflict, the lack of protection became catastrophic. But by then, Japan lacked the industrial capacity to develop and produce replacement fighters in sufficient numbers. The Zero remained in production until August 1945, with over 10,000 built because no adequate replacement existed. Horikoshi expressed profound regret in his post-war memoir, published in 1956. If I had understood in 1937 what I learned by 1944, I would have designed the Zero differently. I would have sacrificed range for protection. I would have accepted lower performance for pilot survival. But we designed for a short war, and the war did not end quickly. Our pilots paid the price for our assumptions. American designers who studied captured Japanese aircraft after the war expressed professional respect for Japanese engineering skill. The Zero was brilliantly executed within its design parameters. The problem was not execution but philosophy, assumptions about warfare that proved fatally flawed. 79 years after Tadayoshi Koga crashed on Akutan Island, the captured Zero remains one of the most significant intelligence coups in military aviation history. Its impact extended far beyond the immediate tactical lessons of 1942 to 1943. The Zero demonstrated that aircraft design reflects cultural values and strategic assumptions. Japanese culture valued offense, accepted risk, and assumed short, decisive conflict. These values produce an aircraft optimized for initial combat effectiveness at the expense of long-term sustainability. American culture valued protection of human capital, assumed long attrition warfare, and built aircraft accordingly. In a short war between roughly equal opponents, the Zero's philosophy might have prevailed. Japanese pilots in superior aircraft might have achieved air superiority quickly enough that attrition did not matter. But the Pacific War was not short. Opponents were not equal in industrial capacity, and attrition became the determining factor. The lesson is not that American design philosophy was inherently superior. It was superior for specific war that occurred. A different war might have favored different choices. But the Akutan Zero revealed that design choices have consequences that extend beyond engineering specifications. Choosing performance over protection meant accepting pilot casualties that Japan could not sustain. Choosing lightweight construction meant accepting battle damage vulnerability that proved catastrophic in long-term attrition warfare. Modern aircraft design has adopted the American lesson universally. Every military aircraft today includes comprehensive pilot protection, redundant systems, and survivability features. Performance is never sacrificed to the degree the Zeros sacrifice protection. The consensus across all modern air forces is that pilot survival justifies weight penalties, because experienced pilots are more valuable than marginal performance advantages. The Zero's legacy is paradoxical. It was one of history's finest fighter aircraft, brilliantly engineered, a masterpiece of lightweight design. But it was also fundamentally flawed, optimized for assumptions that prove wrong, a cautionary tale about the consequences of prioritizing performance over survival. In July 1942, when Albert Knack spotted red circles through fog over Akutan Island, he could not have imagined the chain of consequences that would follow. That single observation, a crash Zero in an Alaskan marsh, would change the Pacific War's trajectory. The Akutan Zero taught American pilots how to defeat the terror of Pacific skies. It validated American aircraft design philosophy. It accelerated tactical innovation. And perhaps most importantly, it provided hope when hope was desperately needed. American pilots in mid-1942 were losing. They were flying inferior aircraft against superior enemies, dying in numbers that suggested eventual defeat was inevitable. The captured Zero did not make American aircraft suddenly superior. The Wildcat remained outclassed by the Zero even after pilots understood its limitations. But the Zero's secrets gave American pilots the knowledge they needed to survive until superior aircraft entered service. When Hellcats and Corsairs arrived in 1943, American pilots were ready. They knew how to exploit Zero weaknesses. They understood the importance of energy tactics. They had confidence born from knowledge rather than fear born from mystery. The result was American air supremacy that Japan could never challenge effectively again. Tadayoshi Koga died in service to his emperor, carrying out orders as a warrior. His unintentional sacrifice, delivering his Zero intact to American engineers, saved thousands of American lives and shortened the war by months, perhaps years. There is tragedy in this irony, but also a strange honor. Koga was an enemy, but he was also a skilled pilot doing his duty as he understood it. His legacy, however unintended, was profound. The Akutan Zero itself is gone, scrapped in 1945 after a ground collision, but its influence endures in tactical manuals, aircraft design philosophy, and historical memory. It remains the most significant captured aircraft of World War II, the intelligence coup that helped win the Pacific War. On Akutan Island today, a simple marker identifies the site where Koga crashed. The marsh where Zero sat for 35 days is still there, unchanged by the decades. Few visitors reach this remote location, but those who do stand on ground where history pivoted, where a young Japanese pilot's death inadvertently gave his enemies the knowledge they needed to ensure his nation's defeat. The marker does not judge. It simply states facts. A pilot died here, an aircraft was captured, the war changed. That is legacy enough. The rest, the tactical revelations, the strategic impact, the thousands of lives affected, speaks for itself in the record of battles that followed. In the end, the Akutan Zero story is one of consequences. Choices made by Japanese designers in 1937, trading protection for performance, led to an aircraft that dominated early Pacific combat. But those same choices, multiplied across thousands of aircraft and hundreds of battles, led to pilot casualties that Japan could not sustain. And the choice by one American aviator to investigate an odd shape in an Alaskan marsh led to knowledge that changed how America fought the Pacific War. Small choices, enormous consequences. That is a lesson of the Akutan Zero, a lesson as relevant today as it was in 1942.